All right, so let's do a little bit of a summary. All right, so we talked about this whole idea, the non-homogeneous differential equation. To say that it's non-homogeneous, what does that mean? It's not equal to 0. It's equal to some driving function or driving force, which in the context of a circuit means that there's a voltage source or a current source in that circuit that allows this thing to respond. So there's two parts of the solution to this thing, right? What are the two parts called?
The natural response and the forced response.
All right. So we got two answers, one in the room and one online that were different but both correct. All right. So there's the transient, which online I heard the natural. So the transient and natural are the same thing, right? And then there is the steady state and the forced solution, right? So the forced solution, I like that term because to say it's a forced solution means that it's basically there is some source in the system that's causing it to respond in a certain way. So if I'm talking about a circuit, right, that means I got a voltage source or a current source that's causing that response. What causes the transient or the natural response, as it was called? Where does that come from?
When there is no forcing function.
Well, even if there is a forcing function, there's still a transient response, right? It's the circuit resisting the change. So naturally, the circuit resists the change, right? And so it can happen even if I don't have a source. I still get that transient response, right? It's the result of what would happen if I had a capacitor that was charged up and I didn't have any sources and just let it discharge. How would the circuit naturally respond to that? All right, so there's always those two parts of a response. I said basically for the inputs we're looking at, I'm basically considering three types of inputs. All right, so the most common things that you come across in real engineering problems is step, exponential, or a cosine. All right, and a cosine and sine are the same thing. And this step input U of t basically means that there's nothing before t equal to 0, and then it's 1 after that. So that basically represents, like I said, turning on a switch. So if I have a switch that connects a source to a circuit, there's nothing before the switch closes, right? So this step function sort of models what that switch does. All right, so we've been talking the last two lectures about having second order differential equations. So second order differential equations should look something like this, where the constants here, B and C, they're always going to be constants, okay? What else should they also be? Anybody know what else B and C should also be? We know that when we try to solve for the transient response, what's supposed to be true about we're going to get what do we call it? The characteristic equation from this thing, right? The characteristic equation, the roots of that have to be what? B and C better both be positive, okay? So that differential equation you could get from writing down some circuit equations, right? This could come out of a KVL or KCL. If you write a KVL or KCL and you get negative coefficients in your differential equations, you did something wrong. All right, the universe doesn't work that way. All right, there better be positive values in these B's and C's. Okay. All right. So if I look at this here, we said our process was that there's three steps. First step is to get that homogeneous equation and to get the transient response, natural response, homogeneous response, whatever you want to call it. And then we solve the non-homogeneous equation, which is to get the particular solution. We use this undetermined coefficients approach. And then we put those two together to get the total solution. What are we solving for in the total solution step here? What are we solving for in step 3? What's left to do by the time I get to that last step? Well, I have the initial
constants of integration.
I'm solving for some constants, right? Using the initial conditions. So there's usually a couple of constants that are left from the transient response that I'm solving for. All right, so that's our last step. All right, so last time I went through, and this is in the notes, basically for the 4 different cases that you could have, what the 4 different transient responses look like. Now, in general, if I have a second order system, my solution always has this form right here. All right, always 2 exponentials. Now, the only caveat to that is if I get into a situation where it's critically damped. Right? What does this mean? S1 equals sigma S2.
Repeated root.
Repeated roots. So two roots that are real and equal to each other. They're not unique real roots. So if they're not unique like that, I have to have two unique exponentials. So you can prove that one way to do that is to multiply by t, right? And that gives me a unique response when I do that. So that would be one exception to this, I guess, where I say it always has this form. But like I said, in general, the critically damped situation really never occurs in practice. And so I stay away from it. I know that's something that you look at mathematically, but I tend to stay away from it. The underdamped, the overdamped, and what I would call the undamped happens a lot. Now, the undamped is where I have two purely imaginary roots. If I had two purely imaginary roots right here, I have an exponential. What does that mean? If I plug in, if S1 and S2 were both imaginary numbers, so one of them would be j omega d, or well, the way I wrote this here would be j times the square root of c. The other one would be like this, right? I'm not going to put any coefficients on there. If I look at those two things like that right there, what is this thing? And what is this thing? Those are vectors, right? That rotate in the complex plane. One of them is rotating in the forward direction. One of them is rotating in the backward direction. Which one rotates in the forward direction? Which one?
The second one.
The forward direction is actually this guy right here. And the backward direction would be this guy, right? But when I have two vectors that are rotating like that, one forward, one backward at the same rate, Euler's identity tells me that I have what? A cosine, okay? A cosine. So in other words, the answer is always exponentials, but if those exponentials are complex, then what I get is a sinusoid. And if I have if it's underdamped, meaning there's a real part, that means that I'm getting a cosine that decays, okay? All right, I'm getting a cosine that decays. So the weird thing about this undamped case is I can actually get a situation where the transient response isn't really transient, actually stays there, okay? Now, the last problem on the homework 5, has a situation like that. And you'll see that there has to be something in that circuit to make that thing not go away. All right, so if you look at the example I give you there in the homework, there's a dependent current source that's in that system. And that dependent current source is a real thing. You can actually build that with circuitry, okay? All right, so anyway, these are our 4 choices. So this sheet is useful to you, hopefully. All right, we said if I had a particular solution where I had a sine wave, all right, that was the input, we had this sort of multi-step process where if I have a cosine as the input, the steady state response is going to be a cosine. All right, so we're gonna look at, there's a very detailed example that I posted online. You go through that video and you can see it. There's actually 2 examples that go through that. One of them with the first order, one of them with the second order. We're going to talk briefly about this again here today, but there's a multi-step process for trying to deal with that. And then I kind of broke out sort of a more detailed set of steps here. So, my step 1, get the transient response. Step 2, get the particular solution. And then I added some steps, and I referred to this in the video that I posted about how you can simplify the equations to be able to get the total solution. All right, so we're gonna look at that again in some detail here today. All right, but I wanted to point out that all this stuff is there in the notes. All right, so this example here that I have is fully worked in a video, one of the videos that I mentioned in the announcements over the weekend. But I want to look at one piece of this, the part that I left off on in class the other day, which is the particular solution piece to this. Okay, so if this is my differential equation, if I was looking at the particular solution, what is my guess for the particular solution in this particular case? What should YP look like? What should YP look like in this case? Yeah, so B cosine omega t plus phi, where I know that omega is equal to 10. The frequency of the input and frequency of the output can't change. But what this says in words is the output of the system can have a different amplitude than the input, and it can be shifted left or right from the input, right? That's what this is saying, but it has to vary at the same rate, okay? So I had sort of a multi-step process for thinking about this thing. And I said, well, I guess the solution, we already did that. We've said a number of times that if I have B cosine omega t plus phi, that is the same as the real part of this rotating vector. B e to the j phi, e to the j omega t. We were talking about complex numbers. I gave that thing, that whole thing here, a name. What did I call that? This whole B e to the j phi, e to the j omega t. What do we call that? The dynamic phasor. Okay. And then B e to the j phi, we called the static phasor. Okay. And in 2112, you just use that static phasor part. You basically, you exploit the result of this process, all right? Which is really what we show when we do this, is that you actually don't ever need the e to the j omega t because it drops out of the math, okay? All right, so there's a couple of steps here. So basically I say we guess this, then I convert the non-homogeneous equation into the complex exponential domain. In other words, I put this non-homogeneous equation in terms of dynamic phasors. Okay. I put it in terms of the dynamic phasors. I substitute in the dynamic phasor for my guess. That leaves me with two equations and two unknowns. Once I get those two equations and those two unknowns, I take the real part of that dynamic phasor and I'm done. Okay, it's a pretty straightforward process. Looks complicated, but it's pretty straightforward. So back to my equation here. What is it? So 4, okay. All right, so I had, this is my equation, what was it? Okay, 4 plus 4 dy p dt plus 3 yp of t equals 4 cosine 10t plus 45 degrees for t greater than or equal to 0, like that, okay? So my step 1 was to guess yp equal to b cosine 10t plus phi, all right? Or that's the real part of b e to the j phi, e to the j 10t, all right? My step 2 is basically to say, okay, take this equation here and put that into this dynamic phasor form. I don't do anything different. Second derivative, okay. Don't do anything different to this side of the equation. What do I change about the other side of the equation? What do I change about this? I don't say 4 cosine t plus 45 degrees. I put its dynamic phasor. What's the dynamic phasor that goes with that? What goes with 4 cosine 10t plus 45 degrees?
That's going to be 4e to the j phi e to the j
Yep.
10t.
Yep, that's it right there. Okay. So what I do then, I said my third step is I plug in the dynamic phasor for this, all right, for my guess. So I get second derivative of, well, let me do that over here. All right, d squared by dt squared, b e to the j phi, e to the j omega t, plus 4 times the first derivative of that thing, plus 3 times b e to the j phi e to the j omega t, all equal to 4 e to the j 45 degrees times e to the j omega t. And I'm purposely leaving it in terms of omega. Omega is a number, it's 10, but I want to leave it in terms of omega on purpose. Okay. All right. So this ultimately is going to lead to two equations, right? One for b and one for phi. What do I do with this? What's my next step from this step? I take the derivatives, right? What happens if I take a derivative of e to the j omega t?
It is going to be derivative with respect to t
Yeah, derivative with respect to t.
is going to be 0 because it's constant.
No, if I take the derivative of e to the j omega t,
It's going to be the same. It's going to be ju e to j
Yep.
omega t.
yeah. The j omega comes down. The t doesn't come down, right? The j omega comes down. And if I did this, n times, right? Let's say it's the nth derivative of this thing. What would the nth derivative be?
J omega to the power n times e j omega t.
J omega to the power n. Basically, the j omega just keep coming down, and the e to the j omega t keeps coming out. So if I take this whole thing and I simplify this guy here, what this is going to end up as is, on the first term, I'm taking a second derivative, right? So I'm taking a second derivative. I'm going to get a j omega to the what power? Second.
Second.
Yep. So I'm going to get a j omega squared times b e to the j phi e to the j omega t plus 4, in this case, j omega comes down once, times b e to the j phi e to the j omega t. This term here, I don't do anything to it. So I say plus 3 times b e to the j phi e to the j omega t. And that's all equal to 4 e to the j 45 degrees times e to the j omega t, like that. Now, what happens immediately from that? What do I see in all those terms? Everything on the left and everything on the right. J omega t cancels out. It's gone. All time dependence is gone. All right. This is why like I said, in 2112, they don't even worry about this idea of trying to equate sine waves to dynamic phasors, because only the static phasor is left. That leads to something called impedance, which you guys probably haven't seen just yet. Maybe you have. All right. But basically, I can exploit the fact that the differential equation part, which is where the time dependence comes in, actually goes away. Right? If I have sinusoidal inputs, in that special case, right, all of the math gets a lot simpler, right? And this equation works out to just be simply, all right, j omega squared plus 4 times j omega plus 3 times b e to the j phi equal to 4 e to the j 45 degrees. So what did I do? I basically saw that there's a b e to the j phi in every term on the left. Okay. So when I look at that, I can rewrite this thing. I write it this way: b e to the j phi equal to 4 e to the j 45 degrees divided by 3 plus j omega squared plus j times 4 omega. I'm going to write it that way. Okay. Now, that is two equations. Looks like one, but it's actually kind of two equations, right? How can I turn that into two equations? How can I turn that into two equations? Right. Well, I could solve for the real and imaginary parts, right? That's a little more complicated for me, because what I really want to get is b and phi. So instead of doing the real and imaginary parts, I can do the magnitude and the angle, right? So I can take the magnitude of both sides, and I can take the angle of both sides, right? So if I take the magnitude of both sides, right, taking the magnitude of both sides, I take the over. So on the left, the magnitude of b to the b times e to the j phi. What is that? B, right? E to the j phi, what's its magnitude always? 1, right? E to the j phi is cosine phi plus j sine phi. Take the magnitude of that, it's cosine squared plus sine squared. What's cosine squared plus sine squared always equal to? 1, okay? So b e to the j phi is, the magnitude of that is just b, right? So how does that relate to the, okay, the term here, 4e to the j 45. I got basically the number 4 with an angle 45 degrees. What's the magnitude of 4 with an angle of 45 degrees? 4, right? What's the magnitude of the bottom? So if I have a complex number divided by another complex number, and I take the magnitude of that, what's the magnitude of one complex number divided by another? So if I have a divided by b, both of those are complex. And I say, what's the magnitude of that? What's that equal to? So the magnitude of a divided by b is the same as what? Yep, magnitude of a divided by the magnitude of b, like that. Okay, so what's that going to be in this case? What's the magnitude of the top? So 4, I think the e to the j whatever screws you guys up, right? If I say 4e to the j 45, that's basically 4 with an angle of 45 degrees is what that is. So if I say, what's the magnitude of 4 with an angle of 45 degrees? What's that magnitude? 4, right? So on top, I get a 4. Now on the bottom, I got real and imaginary part stuff going on here, okay? So I take the square root of the real part squared plus the imaginary part squared. What's the imaginary part of this thing? So yeah, so I have a j omega squared. So if I have j omega squared, what happens if I have j squared? J squared is equal to -1, right? It's equal to the square root of -1 times the square root of -1, right? So square root of -1 times the square root of -1 is -1. All right, so this guy basically is, if I look at it carefully, 3 minus omega squared plus 4 times omega squared, like that. Okay, that's how I can write that out. Okay. Now, if you watch the video I posted the other day, right, I actually just view this as one equation and I let Matlab do the work for me. All right, but it's good for you to be able to see that. So let me add another slide in here real quick.
I have a question, please, related to the derivative for the last slide.
Okay.
Like, do we have the derivative here? It's for products. Do we have to use the product rule for the derivative for b e to the j omega t e to j phi?
Well, okay. So when you look at this thing here, right, you're taking the derivative of this with respect to t. What's true about b and phi?
It's a constant?
They're constants, right? So b e to the j phi is a constant. So if we look at it, the steady state solution, right, is changing as a function of time, but the b is not and the shift is not. Those are constant values. The only thing that's the cosine is a function of time, but that phase shift and that magnitude are not functions of time. So there's no product rule to take in this particular case.
All right, thank you.
Good question. That's something good to clear up. All right. Any questions about this last step right here? All right. Same thing. If I have b e to the j phi equal to 4, remember, e to the j 45 degrees just simply means that it's 4 with an angle of 45 degrees. On the bottom, I have 3 minus omega squared plus j times 4 omega. All right, I got to get another equation for the angle. Okay, so if I take the angle of b e to the j phi, again, to say b e to the j phi means that it's b with an angle of phi degrees. So what's the angle of b with an angle of phi degrees? Phi. Okay, so if I take the angle of that whole thing, right, the angle of both sides, so the angle of the left is equal to the angle of the right. So if I have the angle of some complex number divided by another complex number, how do I deal with that? Subtract, yeah. What's the angle of the top here? 45, okay? And it's phi over here, all right? What about on the bottom there? What do? I subtract it. How would I set this up in this particular case? How would I set this up? Inverse tangent of what over what? Imaginary over real. Now again, omega is a number in this particular case. Omega is 10. Right, I just didn't plug it in there. Okay, so there's two equations. This is equation 2. All right, this is one of the equations. Okay, omega is a number, so I plug in omega, I'm going to get that result. Over here, all right, I got b is equal to this guy. This is the other equation. All right, so I can put both of those in and solve. So what I said, I talk about this in my video, but basically what I do is I created this thing called B complex. So B complex, all right, is basically B e to the j phi. And what I did was I just took here, all right, I said this guy was 4 e to the j 45 degrees divided by, you know, what was it? 3 minus omega squared plus j times 4 omega. I basically took this expression and I wrote it right there. Okay. So I have B complex, which is this thing, is equal to that expression, right? And then I asked Matlab, give me the absolute value and give me phi. All right. From that, I then have my answer. Okay. So my very last step in this whole process, step 5, was take the real part of that result. So it basically says, once I know B and once I know phi, I basically just have to write out for myself that the YP of T is equal to 0.0381 cosine. Omega was 10, so 10t minus 112.5902 degrees. Right? That's, at that point, I'm done. Once I know B and once I know phi, I have that whole thing. Now, you watch that video I posted. It walks through how you get to this final solution. The problem I have with this thing getting to the total solution, I got to add the transient to this, right? But when I have a second order system, with a second order system, I need 2 initial conditions, right? One of them is for y of 0. What's the second initial condition I always have? So one of them is for y of 0. What's the other one always for? The derivative of it, which means I got to take the derivative of yp, all right? So I got to take the derivative of this whole thing to be able to do that, all right? How would I take the derivative of that? 0.0381 cosine 10t. What would the derivative of that be? Because you have to do that by hand, right? Yp prime of t. What would that be? Yeah, so the omega comes out, and because it's cosine, it's a negative. So this would be negative 10 times that amplitude times cosine of this. All right. You should know how to do that. I said back at the beginning, things that you should know how to do. You should know how to take the derivative of sine, cosine, exponentials. That stuff should be back of the hand for you. All right. If it's not, it should be. All right. That's the stuff it's really gonna kill you in later classes if you have to think about those things. All right. Cosine, sine, exponentials, those you should know by heart. Okay. All right. So to plot that, you can look at this example. Again, this is posted and the video goes through it. All right. The important thing is the total solution is the combination of those two things. So in this case, this is my YP, right? YP is just a sine wave, just moving. It never changes. The total solution is the summation of those, right? So the red here is just the transient response by itself. If I plot that, that transient response better always end up centered around 0. All right. And I noticed that by the time I get to steady state, YP and YP, the particular response, and the total response look exactly the same. All right. So after the initial transient, they look exactly the same. Total solution and the transient response, sorry, total solution and particular solution better become exactly the same. All right. If they don't, you did something wrong. Okay. There was a hand raised online, I think. Go ahead. Whoever that was. I saw something about a hand raised. Maybe you didn't mean to. Who was it? Anybody had a question? All right. Okay. All right. So I'm going to go through in a little bit more detail here on this next example, right? Where basically this last part, there's a couple of steps to it, and you can get a general form to the process, right? So it's pretty straightforward how to approach it. Let's look at that example and then kind of walk through it. All right. This one doesn't have, this is a much simpler input here, right? In this particular case, I have U of t. So if I have U of t as my input, that means that if one other way to write this for t greater than or equal to 0, how could I write this expression for t greater than or equal to 0? So it's second derivative of y plus 4 dy dt plus 9y is equal to what? 1. Okay. So it's equal to a constant after t equal to 0 is all that U of t thing says. All right. And I've got my initial conditions. Y of 0 is equal to 3. Y prime of 0 is equal to 0. All right. So what's my first step in this whole thing? What's step 1 for me? Find the transient. All right. To find the transient, the real math way to do this is to set the whole thing equal to 0, right? And I guess e to the st as my solution. So to get the transient, you guys should know by now what's going to come out from that. What thing do I create from this to get the transient response? What do I create from this equation to get the transient response? Characteristic equation. What's the characteristic equation that goes with this expression right here? S squared plus 4s plus 9 equals 0, right? So from this guy, I get the homogeneous equation, which is to say, set the differential equation equal to 0, but I end up with s squared plus 4s plus 9 equals 0, okay? Now, this guy, if I want to solve for this, again, I said the way I try to do this is I use this roots function in Matlab. I say roots like this. All right, and I give it a vector that has the coefficients. Anybody know, how would I put the coefficients in for that? It's in a row vector. What order do they go in? If you've tried it.
First, second, third.
Yep, 1, 4, 9. And it'll tell me the roots if I do that, okay? Now, if I didn't know how to do this, you should have known this back to algebra in high school, right? So S equals what? I do my quadratic formula, right? So opposite of b plus minus the square root of b squared minus 4 times 9 divided by 2 times 1. Okay? Right off the bat, what is this guy? Is he underdamped, overdamped, critically damped, undamped? Which one is he? Underdamped. How do you know it's underdamped? 4 times 9 is 36. So 16 minus 36 is, it's going to be negative, right? So that the term under that square root sign, right, is negative. So that means I'm going to get a complex set of roots. Okay. So if I look at this guy, I don't care what that number is right now. I'm going to let MATLAB give me that number. I don't want to solve for it. I'm going to say that this guy is -2 plus or minus j times omega d. All right. I'm going to call that omega d. All right. That's the result that I get. All right. That omega d is going to be whatever square root of 16 minus 36 divided by 2, right? Whatever that works out to be. But I know that thing, and I call it omega d because the imaginary part is the part that is always going to end up in the cosine. All right. So if I think about what this looks like, right? So what is my transient response? I said, what's my general form of the transient response? So I figured out these roots, but what's my general form to the transient response? Y sub c of t is equal to what? What's the general form of it? C1 e to the S1t plus C2 e to the S2t. All right. So if I look at S1 and S2, S1 and S2 both have, let's write this out, C1 e to the negative 2t times e to the j omega dt. This here would be the first term. The second term would be C2 e to the negative 2t times e to the negative j omega dt. Like that, okay? If I combine those two things, I look at this. So first of all, there's a common factor in both terms, isn't there? What's the common factor in both of those two additive terms? E to the negative 2t. So I get an e to the negative 2t in front of everything. And then I have C1 e to the j omega dt plus C2 e to the negative j omega dt. Now, if C1 and C2 were the same magnitude, what would be true about those two vectors right there? Right, this is a vector here, and this is a vector here. If C1 and C2 had the same magnitude, what would be true about that statement? It wouldn't cancel, but they kind of cancel. But if well, so let's just pretend that they are the same. Let me write it like that. If I have C e to the j omega t, so this is a positive here, and this is a negative. It has the same form as a cosine, right? So I have a cosine with this e to the negative 2t in front of it, which means I'm getting a what's that cosine look like? What's happening to its amplitude over time? As time advances, the amplitude of this cosine is getting what? Smaller, right? By multiplying by e, what's e to the negative 2t look like? Right? If I plotted e to the negative 2t versus time, what's that look like? It's exponentially decaying, which means it's like I've taken the amplitude of a cosine and multiplied it by something that's getting smaller. So I get a decaying cosine. All right. So suffice it to say, if you go through the math on this whole thing, what you end up finding out is that C1 and C2, right, they have the same magnitude. And their angles are opposite of each other. If their angles are opposite of each other, what's true about C2? What do I call that? What's the term I use for that? Conjugate, right? So C2 is always the conjugate of C1. And that's what's needed for this to happen. All right, is that C1 and C2 have to be conjugates of each other. We can prove that. The book proves that. All right. It's not a good use of our time to focus on proving that here. You can sit that through and you can read that proof if you want to. All right. But that's always going to be the case. C1 and C2 are going to be complex conjugates of each other. So if I were approaching this problem, all right, if I were given this as an assignment, what I do is I look at this thing right here. All right. I look at the roots. I get those two roots. And I looked at my general form of this thing, right? I go back to the general form. Actually, I think I'm going to put it closer. Yeah. I look at the general form for this underdamped. I called the real part here of the root sigma, and I called this imaginary part omega d. So looking at this thing, I see that S equals -2 plus j omega d, or plus minus that. So my omega d value is 2.2361. Now, why am I calling that an omega? Why did I call that an omega? Because what's this thing? What does this combination become? A cosine, right? And what's omega going to be? Its frequency, right? That's why I called it omega, because it's always going to give rise to the frequency of that cosine. Okay. So if I go through this process, now for this thing, I got to guess a particular solution as well. Okay. So my equation here was d squared yp by dt squared plus 4 dyp by dt plus 9 yp equals 1 for t greater than or equal to 0. So what do I guess for yp in this case? What do I guess for yp? A constant. So I call it b, right? I guess that it's b. So what's the first derivative or the second derivative or any derivative of a constant? 0, right? So I'm going to end up with basically the 9 times b equals 1, or that b equals 1/9. 1/9. Okay. This one's a lot easier than the thing where I have a sinusoid, right? I get to the b equal to 1/9 pretty quickly. Right now, I get to my last step. Okay. So I combine those two things. When I combine them, they look like this. Okay. Now, when I'm looking at this, I say this is what I end up with, right? I have two initial conditions. One of them for y of 0 and one of them for the derivative. So I got to take the derivative of this thing. Now this guy is underdamped, and underdamped is always kind of nasty, right? So, but if I look at it this way, taking the derivative of e to the s1t and e to the s2t is pretty straightforward, isn't it? What's the derivative of this expression right here? Let's go step by step from left to right. What's the derivative of 1/9? 0. What's the derivative of c1 e to the s1t? s1 c1 e to the s1t. All right. What's the derivative of this guy? c2 e to the s2t. Just s2 times c2 times e to the s2t. Right? Pretty straightforward what that process is. Right? So I have everything I need at this particular point to be able to combine the things. I have two unknowns. What are my two unknowns at this point in the process? S1 and S2 are known to me, right? Those are roots, right? I don't like writing in the numbers. I like keeping it in terms of variables because, again, I can use the code. And when I keep it in terms of variables, I can just track a process a lot more easily than I can when I'm looking at numbers, right? So I don't like hard coding stuff. I like keeping it in terms of the variables because then I can check to see that I'm following the right process a lot more easily, right? That's why I always do it that way. And I recommend that you start thinking that way too, because the process is the same every time. It's only the numbers that are different. If you jump to the hard numbers right off the bat, you're more likely to make a mistake, all right? Or less likely to be able to track where your mistakes happened. What are the two things I'm solving for here? C1 and C2. So I got two equations and two unknowns. This is one of them. This is the other one. Right? My initial conditions happen at t equal to 0, right? So if I look at this here, if I plug in t equal to 0, what do those two equations become? Y of 0 is what, and y prime of 0 is what? What happens when I plug in t equal to 0 over here? My exponentials become what? They don't really drop out per se, but what do they become? Yeah, e to the 0 is what? 1, right? So I get that this is 1/9 plus C1 plus C2. What do I get for the one on the bottom? The derivative. What's that equal to? What's that equal to? Y prime of 0. What happens when I plug in t equal to 0 into this thing? Yep, S1 C1 plus S2 C2. Now, in general, what I'm trying to say, I guess, is there's a more general way of looking at this. As you guys would like to get to kind of general formulas. The way I look at this is y of 0 is equal to the particular solution plus this derivative. Or what I'm going to say is yp of 0, whatever the particular solution is at time t equal to 0. And then whatever the derivative of that is at 0 plus S1 C1 plus S2 C2. If you watch my example video, when you get into the problem, you have a second order system and you have a cosine for your particular solution, then my derivative is not 0. My derivative is equal to something, right? I got the derivative of a cosine of something. That's going to be a value that's not 0, right? Most likely. And so in general, this is what this guy's going to look like. Okay. So, and these are things, this side, these are numbers that need to be given to you, right? Those need to be given to you. Yp of 0 and yp prime of 0, you need to solve for these or compute them. All right, you need to compute these. Now, for a constant, that's super easy, right? It's 1/9 and the derivative of 1/9 is 0. But if I had a situation where, it was a cosine or something like that, then it's nasty. All right. But you still gotta compute it. Okay. So I put all those together. What should I do with that? I got 2 equations, 2 unknowns. Simplest thing for me to do is to do what? Put them into matrix form. Right? Matlab is totally set up to do that in matrix form. So I recommend kind of setting it up that way. So in this particular case, I gave it kind of a sub-step here, right? Plug in the initial conditions. So the actual values I gave you at the very beginning of this problem was that y of 0 is equal to 3 and y prime of 0 is equal to 0. Right? Those are the hard numbers I have. All right. So what I do is I set this equal to what I found on the previous slide. S1 C1 plus S2 C2. And I try to get this thing into a form that looks like this, right? So I rearrange these here. So I say I have y of 0 minus whatever the particular solution is at 0 has to equal C1 plus C2. And y prime of 0 minus the derivative of the particular solution at 0 equals S1 C1 plus S2 C2. Okay. So when I look at that, the top equation here becomes the top thing in this matrix. The bottom equation becomes the bottom row in this matrix. So over here, so right here, this guy would be y of 0 minus yp of 0. And this guy would be y prime of 0 minus the derivative at that point, like that. Okay. So what I do is I go into Matlab and I basically set it up like this. Okay. I set this up where I wrote in these 2 guys here are my initial conditions. Right. So I set up 2 variables, y underscore 0. Right. This is my initial condition for y. Then I wrote y underscore prime underscore 0. That's my initial condition for the derivative. And then I basically set up this system of equations right here where I called this B, if I look at this carefully, right, this is the initial condition minus the particular solution at t equal to 0. And then this is the derivative at t equal to 0 minus the derivative of the initial condition, or the derivative of the particular solution at t equal to 0, right? So my particular solution was 1/9. Its derivative is always 0. And then I wrote in here 1, 1, s of 1, s of 2, and I go through this solution process, all right? There's a couple of examples online that have this for me, all right? What I end up with here is I solve for my C values, okay? C1 and C2. Looking at those C values that come out of this, what's true about those two numbers right there? What do I call those two numbers? They're what? They're conjugates of each other, right? Just like I said they were going to be. They had to be conjugates, right? So they end up being conjugates of each other. What I do is if you look at my general form of the solution in this case, it's underdamped, right? So this was the form I had. When I look at that, this whole thing becomes this, right? 2 times the magnitude of C1. And then I have this, the angle of C1 pops into the cosine. I used Euler's identity to get from this step to this step. And I'm telling you that you don't need to go through and do Euler's identity every time. This formula will work for you, right? So looking at this, looking at what I got to right here, right? What I see is that I have 2 times the magnitude of C1 times cosine of omega dt plus the angle of C1. So looking at this, right? What I would say is that what's the magnitude of this guy? It would be 2 times the absolute value of C1. So I did the absolute value of C. That means that this guy here is the magnitude of C1. This guy right here is the magnitude of C2. So this becomes 2 times 1.9379, all times cosine of omega dt minus 41.8103 degrees. It's the top one because this one is C1, okay? The angle of C2 is its conjugate. Remember, this whole idea that I have 2 rotating vectors, the 2 rotating vectors always have to be conjugates of each other, okay? So we're just exploiting that result here and kind of jumping straight ahead to our solution. All right, so I end up with that as my total solution by the time I'm done. And I would go into Matlab, and here's how I would enter it, right? So I have a time vector, right? I'm usually giving you guys a time vector. One thing I did here is I calculated what the period was of the cosine. So I took the omega d value, which is the frequency in radians per second of that cosine. I did 2 pi over omega to get the time step. And I plotted it for 3 periods in steps of a period divided by 1,000. All right, now it's hard to see 3 periods here because the amplitude of that cosine is getting smaller the whole time, right? There's this e to the negative 2t multiplying the whole thing. All right, so this is how I would, and notice how I did this too, right? There's one important thing I wanted to throw out here. You guys are going to get screwed up by this, but I have an e to the negative 2t times a cosine of omega dt plus phi. All right, let's just call it that. The way Matlab deals with this, right? T is a vector, right? So e to the negative 2t is a vector, right? Cosine omega dt plus phi is a vector. Can I multiply 2 vectors like that? Does Matlab like it if I multiply 2 vectors? What am I trying to do? I'm trying to take every value at time t in this exponential and multiply it by the value at the same time in the cosine vector. Is that
Only
what this
dot product?
What's that?
Only with dot product?
This would require not what we call the dot product, but you got the right idea. It's the dot multiply.
Yeah.
Right. It's how we do it. It's the element-wise operation. All right. Some of you are going to blow up your memory when you try to do this. All right. You got to make sure to have that dot multiply here. Right. Because you're trying to multiply 2 vectors. Okay. So if you look at the expression that I wrote out here, this expression that I wrote out is basically in terms of the values that I have here, okay? So looking at this here, which one of these, the red or the orange, or I don't know, that's yellow or orange, but which one's the particular and which one's the transient, which one's the total solution? From looking at this, you should be able to tell which one's the transient, which one's the total solution. What better happened to the total solution? What does it always have to equal if time advances? The total solution better equal to steady state. So basically this orange here eventually sits on top of the blue. This guy is the particular. This one here, that yellowy, is the total. And the red one here is the transient response, right? The transient response settles around 0, whereas the total solution settles around the particular. Okay. All right. No more examples of that. All right. Lots of differential equations. You guys should know pretty much how to deal with the differential equations. This is just a slightly different way of looking at them than you did in your differential equations class. All right. I'm not going to spend too much more time on them. What I am going to do is talk a little bit more about how do we deal with numeric solutions. Okay. So it's going to introduce the concept a little bit here in the last couple of minutes that I have. All right. So where would I use numeric solutions? So basically, in the real world, very often, right, in the computer, you have to solve differential equations. All right. So a couple of examples, right? So I gave a couple here. One of them would be a circuit simulator. So you guys use, you guys haven't used SPICE, but you probably use multi-sim, right? Multi-sim is a circuit simulator. So there's code in there where it doesn't, behind the scenes in that code, it's not guessing that, okay, well, I've got a differential equation. I'm going to guess that it's e to the st and all this. It doesn't do that. It solves it numerically. Right? There's a process to convert the differential equation to something digital. Right? Another place where I would use this a lot would be digital control or signal processing. So if I had an embedded system, for instance, I might need to take the differential equation in some way and use it in some useful way. All right. So an example is this guy. All right. So what I have here on the bottom, all right, this is an audio signal. All right. So if I looked at an audio signal on an oscilloscope, like a true audio signal, this is the kind of thing that I would see. All right. Is essentially it's sine waves that are changing their amplitude over time. Okay. So I actually have this in Matlab. So Matlab can play sound files, and you're going to deal with that in your project. All right. So I'm going to read in. So there's this audio read, basically reads in a wave file. Okay. So I'm going to do this here real quick. All right. So I'm going to run that, and then I have two sound files. So there's this image right here and this image right here. This one on the top is a corrupted waveform. All right. In other words, that's some noise added to it. Okay. So if I'm going to play the two of them here real quick. So the first one is the top guy. So hear that. All right. So it's a sound you might have heard before. That's sort of the background is Handel's Messiah. It's whatever. It's a signal that MATLAB has built in as a wave file. Okay. What is that kind of? You may have heard there's that kind of hum on top there. Actually, most of what you're hearing is the hum, probably. Any idea what that is? Any idea what that is? 60 hertz. Yeah. That's a pretty common signal to have kind of messing up your waveforms. Why would that be a common signal to have messing up your waveforms? Yeah, so somehow the power signal can screw up your audio from time to time, right? So one thing we're going to talk a little bit more about later in the semester, it's hard to look at a waveform like either of those two waveforms. Even if I zoom in, it's hard to really look at them and know what's going on. So there's a tool we're going to use called a Fourier Transform, right? A Fourier Transform tells me where there's sine waves, what frequencies are there sine waves in there? So if I took this thing called the Fourier transform and I looked at this, which is what's shown here on the right side, right? I see there's a big spike right here at this particular frequency. That's at 60 hertz. There's a lot of 60 hertz on top of this. So one of the things I can do is I can design something called a filter to take that file, and I can basically take that file and clean it up. So if I looked at this picture right here where I have a signal at 60 hertz, where does it look like most of the real stuff is? This is my noise. Where does it look like most of the real stuff is? Yeah, so this stuff out here is the real stuff. This is the real signal. So what I want to do is I want to build a filter to get rid of that noise. So what I want to do is I want to pass the high frequencies. In other words, I want the high frequencies of this signal to pass through, and I want to get rid of the noise, which is a very low frequency thing. All right. So one way to do that would be that if this signal, this corrupted signal I have here on top, if that was a voltage that I could play out of a voltage source, I would put it through a circuit. And that circuit could clean this thing up. From this circuit, I would get a differential equation, right? That differential equation I can turn into code. And that code can do the filtering for me. So if I look at this, and we'll look at this again at the beginning of class on Wednesday, but basically I converted that differential equation somehow to a for loop. And then what I did was I used that for loop to clean up the code. And so if I play the cleaned up version of this, so here's the original. So I hear that 60 hertz hum. And if I do the cleaned up version of it, that hum is completely gone, right? Yeah. So how did I do that? Basically what I had to do is I had to write a differential equation for saying, okay, I know I can build a circuit that would clean that thing up. If that noisy signal was a voltage, I could build a circuit in the lab that would clean it up. Now what I want to do is I want to map that circuit into some code so that if I had a wave file, I could process. Right? That's the kind of stuff that you do in digital signal processing, right? Which is a good computer engineering sort of problem, which is what we're going to try to work on as part of the project. Okay, so we'll talk about how to make that mapping on Wednesday.